The CEO of Google recently said, machine learning is a core transformative way by which we're rethinking everything we're doing. Why? Because it's self-programming, handles complex patterns such as voice recognition, image recognition, spam data analytics, so on and so forth. But even he says we're in the early days. Why? Well, that's because machine learning is a black box. Cannot really be sure what it's doing. It requires a lot of guesswork and prone to embarrassing errors. Recently, a group from Google showed that after they trained machine learning to recognize several patterns, such as bus, they were able to take an image of the bus, add this distortion here, and now it recognizes as ostrich. So it's not doing recognition the same way as humans do, and it's really hard to understand why. That's why even Google, with a huge amount of resources, sometimes releases embarrassing AI. We've developed a method that reduces these problems by making the connections clear box. It's possible to see what are the expectations of the network by just looking at it. And this reduces quality assurance cost and potential embarrassment. It is easier to update, reducing engineering time and computational costs, and it's better at learning data, which reduces the computational costs, increases capability, and all of this reduces the development cycle time. The key in this algorithm is how optimization is done. Now, optimization is the process of trying something, evaluating, seeing if it fits well, modifying, trying again, see if it fits better, and so on and so forth. You can think of a jigsaw puzzle as an example of an optimization. You have the final picture and you have all these pieces, and you try to match them. Now, recognition algorithms have a learning phase and a recognition phase. And the machine learning that's used today is done as follows, where X is the inputs, Y is the outputs, and W is a set of weights that are multiplied to give the answer. Thus encoding what I call uniqueness into weights. And this is done by optimizing during learning. And this is virtually all the algorithms that are out there, including deep learning, backprop, convolutional networks, recurrent networks, support vector machines, so on and so forth. All of those optimize during learning to find the best set of weights in order to perform recognition in this form. But the problem is that optimizing these weights makes them black box. They're optimized to perform this recognition, but you no longer have access to the internal representations. And this is well known. Second, optimizing over the training data is computationally intensive. And for any update, training must start from the beginning. Now, determining uniqueness is essential to perform efficient recognition, and let me give you an intuition. So, in order to optimize weights to recognize Q's and O's, well, in this training instance here, this diagonal is unique, therefore important. So for the weights to recognize Q, the network would increase for the diagonal feature and decrease for the circular feature. But the problem is that uniqueness changes with context. So for this training instance, well, now the circle is the unique feature. So then the weights would decrease for the diagonal, increase for the circle. But you cannot learn uniqueness for all possible contexts. Even if more and more data is added, it cannot predict every possible context. So is this the best way to do things? And beside, the most relevant context is during recognition, not during learning. So if stripes were learned to be the most unique feature for zebra, well, a method would be in big trouble if there were a lot of stripes in the image in the context during recognition. So I suggest instead that uniqueness is determined during recognition when the context is available, and this is done by optimizing during recognition. Now this is to determine the activation, the final solutions, like in the machine learning algorithm, while estimating uniqueness, not to learn the weights. Now there's only one thing to optimize during recognition, and that's the current test pattern, which then results in a large reduction in computational costs. And it's possible to learn the expected patterns without uniqueness, which then makes the weights clear. I'm going to demonstrate the ease of modification, the ability to recall, and a bit of brain-like activation. This first demonstration will be on the levels of ones and zeros. Here we have the inputs, test pattern, the test sound, and so on. Here it'll be just in numbers. Here you have the weights of our algorithm, and here have the weights of a traditional machine learning method. So here are all the nodes that it can represent, and here are all the inputs. And it's the same here. So there is a one-to-one correspondence for both algorithms, but you're going to notice a big difference. So this is not very interesting. I'm going to add a new node and a new feature, and I'm going to say, let's say we want node 1 to be interested in pattern 1, 0, and node 2 to be interested in pattern 1, 1. That means when the input is 1, 0, node 1 should become active and say, hey, this is my pattern. When the input is 1, 1, node 2 should say, I'm active, this is my pattern. So in order to make a traditional feed-forward method, traditional machine learning method, to do exactly the same thing, you would have to learn these patterns, and this is the weights that will perform that recognition. So now what I want to show is that with our algorithm, this is all you have to do here. All you have to do is tell it, what are you expecting? And that's enough to train the network. And to show that, I'm going to run our algorithm here. And what it's doing is it's showing that here, this is the activation of node 1. And here, this is the activation of node 2. And it's showing that node 1 is active, and it's saying this input here is pattern where node 1 is active and node 2 is not active. This is the pattern for 1, 0. And after we've calculated these weights, we can get the same response from the traditional method. Now we can change the input to 1, 1. And you see here that the network responds and says this is the activation for node 2, and node 2 is active, and can do the same thing with the feed forward, and you get the same. Now the difference is that even while this is running, we can add a new node and new feature here, and let's do that. Let's say we want a new node and we want it to be interested in pattern 1, 1. So even while it's running, we add this here, and that's all we have to do. We've just added a new node. When the input pattern will be 1, 1, here it will recognize as node 3. So let's do that. Let's put the input pattern 0, 1, 1, and it recognizes as node 3. Now if you wanted to do the same thing with the traditional methods, you'd have to retrain the whole thing from the beginning. And when you do, you get this matrix right here. And when you calculate, you get the same answer. But this is a harder way to do it. Let's show this even more. Let's go back to the pattern 1-1 here, which is pattern 2. Let's say, you know what? I don't think 1-1 is the ideal pattern for node 2. I think it's actually 1.4. So I can put that in here. And pattern 1-1 is no longer the ideal pattern for node 2. So the network no longer recognizes it as such. Now, when I put 1.4 here, it recognizes it. But when I put the old pattern 1-1, that's not the ideal pattern. Now, if we wanted to do the same thing with the traditional method, well, we'd have to retrain it on everything from the beginning. And notice when I'm going to press the retraining here, notice what happens to all the weights. They change. And they change without real rhyme and reason. But when you calculate, you see you get the same expectations here. And if I change this to 1.4 now, and I calculate here, I get the pattern for node 2. And the thing is that I can also more easily add patterns. So here I set it up where I'm going to add 7 more nodes with 30 input features all randomly generated. And I can just click right here and it automatically adds it. And you can see what are the expectations, for example, for node 4. It's expecting 8.14 for input 1, this for input 2, so on, and you can scroll through everything that it's expecting. If we wanted to do the same thing with a traditional method, we'd have to train it on those patterns. And this is what comes out. Now, if we want to look and see what node 4 is expecting, well, we can't really tell. But if we load the pattern here for node 4, which is these, and you'll notice here, this is loaded here, you'll see the network recognizes this as pattern 4. And you also see this jumping up and down. This is actually indicative of what you see when you record neurons. When a pattern is changed, you see this activation and then it's this going down. Now, again, here you can see the expected patterns. Here you can't. You don't know what is the expected patterns. But when I calculate, you get the same response. So it recognizes pattern 4, and I can change that to, let's say, load pattern 9. You get the response here, and you can calculate the pattern 9 here as well. Now, an advantage here is that we can add things and learn it really quick. So let's add, this is the maximum that this visual display system can take, so let's just add that to the network. So now we're adding about 1,000 nodes here, and it's still recognizing pattern 9. Now we have 1,000 patterns. That's it. It's now going to recognize any of these patterns that we load up. So let's load up pattern 900. It's going to recognize pattern 900. Now, if we want to do the same thing with the traditional method, we'd have to train it on this. But I want you to notice how long it takes. So I'm going to hit the button here to train it and watch. Training, 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 training. There we go. So now it has learned that pattern, and now it'll also recognize. But you see the differences here. And as the data sets grow bigger and bigger, this takes longer and longer compared to this. Now I'm going to ask, is it scalable? What we've done is increased these random patterns and trained it on bigger and bigger and bigger networks. Here we have the computational costs for this. So we did it on a small laptop that's actually equivalent to a modern day high-end cell phone, which is showing the type of learning that can be done remotely. So what we're going to do is we're going to compare algorithms, but all of them have the same hardware and have the same limitations. So first, we started with the SVM. We trained it on 10 nodes, 100 features. Then we kept on training, so on, until it ran out of memory at this level. Then we figured another way to generate the feed-forward weights, the simplest possible method. And we were able to go all the way up to 20 million, and then the system ran out of memory at 20 million. Using our method, we're able to continue until 120 million. So in summary, you can see this is the computing time that it took to learn, and ours remained fast, going out all the way to 120 million. Now, looking at recognition costs, well, feed forward is fast, but we could only train it up to 20 million, and then it ran out of memory. With our method, we could continue all the way up to 120 million, and beyond that, the random number generator ran out of memory, so we don't really know what was the limit in this system. We then wanted to compare with a more limited k-nearest neighbor algorithm that basically takes all the data, compares it with the input, and finds the distance and finds the piece of data that's closest. And when we did this, you can see the algorithm increases, and this is the computational cost per test. It increases significantly compared to our algorithm that's doing an optimization during recognition. In fact, when you draw linear lines, you see this is super linear. It's growing faster than this algorithm, which is sublinear. So I said that you're able to see the expectations. You're also able to see what the algorithm is thinking. To demonstrate that, here we have a network that's trained with MNIST, character recognition from the post office. So here we have the internal representation of the network. It's been trained on all numerals. Here is one of the test patterns from the numerals. And here are the features, the darker, that were most useful in determining what pattern the network thinks it is. Here it determined to be pattern 5. Now, I've slowed the whole network down so we can see how it's working. So every time I hit a button here, you see it starts with the new pattern, and it internally determines what's the best fit by generating an internal image of what it thinks it is. And then it gives the output. So this is the internal image that it's thinking. This is the pattern that it got. And these are the parts of the input that were most important to get to that. Here's another case. Here's another case. Here's another case. And here's actually one that it recognizes wrong. Here's another digit. So with this algorithm, you can understand internally what it's doing. And you can use this information to then adjust, how to scale, how to rotate. This gives you a rich feedback on what to do next. And that leads us to our next demonstration. We want to develop a smart image recognition with using all of these features. So here's an example of recognition of images for a customer of ours. What we do is we'll drag an image here, and our network will recognize. And we can drag rotated images and so on. This network is set up with 13,000 images using one GPU. So this is also not an ideal computer, but you see it works very fast. And so we want to expand on this. Thank you for listening, and we hope you will join us in this endeavor.